Hello. There is Katie, and there is Claudia. Hello, hello. Uh, actually, am I on mute? No, I'm not. Hello, Claudia. All right. Oh, that's a double hello. And sorry, I'm going back. And hello, Shy. And good afternoon, Alexis. And good afternoon, Katie. That's a double hello from Katie. And good afternoon, Brandon. And good afternoon, Maria. That is a double hello from Maria because there she is live in multiple dimensions. Good afternoon. Oh, and that's Maria. Okay. Hello. And who else? Okay. Hello, hello. And hello, Eric. And hello. And more people are coming. And hello, Josephine. And I feel and there goes the garage door, but that's not on Zoom. And okay, I'm just waiting. I'm just letting people in. Da, 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 da. And I don't think I love that. What is it called? Like 8-bit, the Alexis avatar. I feel like it's like a my God, I forget what those Mario flowers are called, but it's like a Mario flower combined, like but taken from Minecraft. But I know it's neither. I'm just like projecting my own. But oh, and there's Paulina. Hello, Paulina. All right, all right. Hello. Okay, excellent. Oh, 8-bit. Yes, yes, it was. Yes, it was. It was the era. It was. Don't even get me started. When I was okay, good afternoon, Jenna. Good afternoon, Stephanie. Oh, yes, when I was young, Mario was but a twinkle in Bowser's eyes. That makes no sense. Mario was but a twinkle in Clive's eyes, and Clive was one of the 4 enemies of Pac-Man. I'm sure you all know this. Inky, Binky, something. And Clive. Anyway, all right. Good afternoon. All right, we're ready to roll. We're just about. Let me switch. But no, I really did play on tabletop versions of Pong. I do have to admit, I am of that. Okay. Um, okay. Okay. So what we're gonna do right now is go straight back to homework 8. We're going to continue with the duck in the elevator. I believe that's where we are. Stop me if I'm wrong. I believe, yes, I believe we're at the duck in the elevator. Bear with me we may not do every single part of it, but we should do a little bit more. The last thing we concluded, the main takeaway of the last part of the duck is that the normal force up from the floor of the elevator, the normal force exerted up on the duck is doing more than supporting the weight of the duck. Like that's the key. Like the point is honestly that and I'm just pulling it up right now. The last point, I mean, as in concept, was that we don't want to fall into the misconception of believing that normal force necessarily always has to equal mg. And we'll see that even more in the other problem, in the next problem that Claudia asked about last week. The normal force sometimes has literally nothing to do with mg, like if the normal force is pointing to the side, which it certainly can. Here with the duck, the normal force has something to do with mg. The key, well, here, okay, I'm gonna, sorry, just get going here. So this is homework. Oh, sorry, wrong call. Well, fine. Homework 8 continued. And the problem that we were doing continued is I did this every time, is the duck problem. And that is problem 4. I know someone's here. Bear with me for a second. Oh, that's Logan. Hold on. Problem 4. The duck and elevator continued. Okay, Logan, hello. Sorry. Okay. Well, all right. More people. Okay. So we did part A. I would say the main takeaway of part A is the following. Okay. The takeaway from part A was that as long as that duck is standing on that normal force, the normal force up minus the weight down equals the MA of the duck. Sure, if A is 0, if the duck is just standing there, then normal force equals the weight. But as long as the A is something other than 0, then the normal force doesn't equal the weight. As long as the A was greater than 0, the normal force up was greater than the weight down, and i.e. the floor has to not only support the weight of the duck, but make sure that the duck accelerates up. Like that's what we concluded last time. Now we're going to go to part B and part C. I will say part B, a couple of people already asked, Maria, Paulina, Claudia, Katie, a number of people asked about part, and maybe some of it was private, I apologize, but people are asking about part B. Yes, to cut to the chase in part B, if the elevator is accelerating, okay, do I just want to answer this? Yeah, I'll just summarize the answer to part B. I mean, we talked about it. Part B, it's all, you do it all analyze it all the same way, but then analyze as in part A, but then notice a contradiction in signs regarding N, right? Like if you do it exactly the same way as A, if you assume that up, or if you decide that up is positive, I keep mixing my colors. If you assume that up is positive, or if you choose, I should say, that up is positive and down is negative, and so then you start and you do the free body diagram and start proceeding just as you did in part A, we find that N is less than 0. Now, it's not that N can't be less than 0, period. Like that doesn't contradict the universe. But if we already started with the assumption that greater than 0 means up, and we wrote N minus mg equals ma, and then we got a negative number for N, that's a contradiction. That means we're finding that the normal force is pointing down. But we found that it's pointing down based on the assumption that it was pointing up. So something is wrong there. I'm talking about part B now, okay? I'm saying if we analyze part B the same way we analyze part A, which we should, I mean, it's all the same physics, then what that means is there is not contact between the duck and the floor, right? And part of what we're trying to say here is, and therefore, the normal force must be 0. I know someone else just came in. Hold on, sorry, I'm going back and forth between. There it is, Chris. Okay, there she is. Right. I mean, this is like actually kind of a subtle. This is a subtle point. It could keep you up at night if you're not careful, or if you want to be up at night for some reason other than the state of the world. This one provokes a little thought, but you can leap out of the mess by, and this is what I think the people that were asking about this were saying last week. Like, if the elevator is accelerating down, if we're told, again, I'm in part B here, folks, for anybody who just joined us. If the elevator is accelerating down at a rate of 50, and it should say 15 meters per second squared. I do apologize for that. That is a typo. But if the elevator is accelerating down at a rate of 15 meters per second squared, that is greater than the free fall rate like due to gravity near the surface of the earth, right? So again, we're talking part B here. In part B, according to the facts, the elevator accelerates down at a rate greater than free fall. Therefore, greater, three dots means therefore, three dots like that. Therefore, greater than the duck. So physically speaking, so there is no contact between the two, between the duck and the floor. So there is no contact between duck and floor in part B, right? So then there is no normal force. Like then the normal force is, oh, well, and it like totally, it sort of guides you through this in part 3. Right. So why are we even bothering? I'm going to go on to part C in a second, but why am I bothering with this? One, this is meant to reinforce that the normal force, by definition, is push from one surface onto another, is a push, a contact push from one surface onto another, perpendicular to the plane of contact. If no contact, no normal. If no surface contact, I should say. If no surface contact, no normal. Why I'm saying that? I'm saying there have to be two surfaces pushing against each other for there to be a normal force. If there isn't two surfaces pushing against each other, there isn't a normal force. If there are two surfaces pushing against each other in whatever direction, then the normal force pushes in that direction. And by that, I mean the against direction, like the pressure direction, the direction that is perpendicular to the plane of contact. I'm saying this over and over again, really, because the normal force is super important in physics. It comes up a lot in physics, and we often have to calculate it, particularly in order to calculate friction. So like it is really important. It's really central. It's really vital. It's a thing we often have to calculate, but because it's so important and so vital, it comes up so often, and because it's called normal, it easily fools everybody into thinking that it's always there automatically. Like what I'm just trying to say again for the 80th time, just because this because it's like a thing, it's like a big sort of issue in learning physics and teaching physics, is that normal doesn't mean always. Unconsciously, it's really easy to think that it does. And normal does not mean that it normally equals like anything. It doesn't. Normal means perpendicular. It means perpendicular contact between surfaces. If there ain't no surfaces, there ain't no normal. If there are surfaces, then there's a normal. Then we have to calculate what it is. It is different magnitude in every different situation. And then from it, we get the friction. So like this whole problem with the elevator, I will go on in a second. I know I'm getting myself all in a dither, whatever that means. But sort of the part of the purpose of this elevator problem is to like drive home how to calculate the normal by applying F net equals MA to the axis that the normal is acting along. And we do that always sort of first. Whenever there is a normal involved in the problem, we try to do that first, look at that axis first, because then quite often there's then friction on a different axis. So we use the normal information, the normal magnitude from one axis, in analyze, in plugging into friction for the other axis, and that's how we put everything together. Like that's like the habit, that's the idea of this. So what it's just trying to say right here is there could be a situation where there's no normal at all, and like and then if that's the case, I'll finish the problem. Then we just use all the other facts in the problem. But I want to say one other reason. So I'm going to finish the problem, but like I just wrote so what, right? And I wrote number one, this reinforces blah blah blah. There's another thing that I sort of hate to. So what continued? I mean, this I don't want to dwell on, but of course I accidentally probably will. So what continued? Objects. There's no rule to prohibit objects from free falling. No, sorry, that's not true. There's no rule to prohibit objects from accelerating downward at a rate greater just to be clear on one other thing, like 9.81 meters per second squared, 10, whatever you want to call it. That's the rate at which things would accelerate down if left alone, if there were no force acting on them other than their own weight, i.e. gravity. But of course, we can hold things still. We can oppose gravity, right? Just to be clear again, if I put a table underneath an object and support the weight of that object so the object doesn't fall, I'm not getting rid of gravity, right? I'm introducing another force called the normal upward force of the table to add into the general mix of forces, to add into the sum of the forces on an object, and ultimately yield a net force of zero. Right? Like you don't get rid of gravity just because you push something up, and you can push something up just enough to support its weight, or you could push it even harder to send it accelerating up. Well, similarly, you could pull something down. There's no rule that we can't pull something down. And if we pull something down, we can pull it down at whatever rate we can. Gravity's not a threshold or like a limiting factor on pulling things down. So this elevator can go down faster than gravity, right? And similarly, like a helicopter could go down at a rate faster than 9.8. It could go down at a rate of, say, 20, like it does in that problem on the midterm exam. And if it goes down at a rate faster than 20, then if you compare that rate to something that's in free fall, the helicopter will go down faster than the thing in free fall. If they both initially so if something's at the bottom of a string or something's being carried by a helicopter and it happens to be going up at a certain moment, but accelerating down at a rate of 20, and you like release the package or whatever, both of those objects will continue to go up until they run out of velocity, but they're both going to be running out of velocity because they're both accelerating down. If the helicopter is accelerating down at a rate that's greater than the rate of gravity, it's going to run out of speed earlier than the package, and it will go, eventually it'll be going down at a greater rate than the package. So I guess I'm just saying, I mean, of course, I know some of you have gotten back, some of you haven't gotten back, but just so, I mean, we'll talk in more detail when everybody has them back, but like, there's no rule that says a helicopter can't go down faster than a package. If it's accelerating down at 20 and the package is accelerating down at 10, then the helicopter is going down faster. And that's what's happening here in the elevator. The elevator is going down faster than the duck. So the duck experiences no normal force. So the normal force in this case is zero. I'm going to go on to the next, that's a summary of question B. I mean, sorry. Let me do like part 4, the math of part 4. So B part 4. How far will the duck have traveled after? How far will duck travel in 7 seconds? Okay, assume that the elevator has a ceiling, that the duck can end up above the elevator. So this is very much like what happens to the helicopter in the exam problem. So the duck is in free fall. The duck so for the duck, so its acceleration is g, which equals 10 meters per second squared. Now I'm going to call for this down positive, because the duck only goes down. There's nothing's going up in this situation. So I might as well call down positive. So y equals 1/2 at squared plus v naught t. And what's v naught? Situation is the same as above. The duck, the elevator, and the initial velocity. The initial velocity is 50, but it's up, right? So yeah, the initial velocity is 50. Oh, so actually, well, I'll make that negative, since I already said. Right. So, right, because I mean, and maybe you could make the other choice. Either one's fine, but I didn't realize anything was going up in the problem, but it is. So 1/2 times 10 times 7 squared plus, now I have to make it negative 50 because it's going up, times 7, right? So we get 49 times 5 is 245, I believe. Right, 49 times 5, yeah. Yeah, minus 350, right? So we get negative 105. So the duck goes up 105 meters. That's the answer to, unless I made a mistake, and you can tell me, and I'll look in the chat in a second, but the duck goes up 105 meters. And again, this is just trying to reinforce also right here. This is old kinematics thing. Like that part isn't really about forces. That's just a free fall problem, that we could have asked a month ago, and I guess we did. It's just trying to reinforce the big difference between acceleration and velocity. The thing is accelerating down, it's in free fall, but it's, as one of our homework assignments was called, it's free falling up, right? Because free fall doesn't mean you have to be moving down. It means you're accelerating down. If you basically, this is what happens if you throw something up in gravity. If you throw it up, it goes up for a while before it runs out of speed, and then it starts coming down. The while hasn't elapsed yet. I just want to think for 1 second. And someone's here. Sorry, 1 sec. And is there anything in the chat? Okay, no problem. Thank you, direct chat person. No problem. Hold on, let me just think for 1 second now too. Oh, yeah. Sorry. Right. So, okay. Let me say that a little bit more clearly. I mean, I still agree with this answer, but the duck has started coming down, but it hasn't come back all the way down to where it was released from. That's really what I'm trying to say. Like, let's be clear. And I will move on in a second, but the duck was, in effect, thrown up at a rate of 50. Now it's losing 10 every second. So it's going to take 5 seconds before runs out of speed entirely. And then, right, because 50 divided by 10 is 5. So, and then it's going to take another 5 seconds after it's run out of speed completely to come back to where it was thrown from. It would take a full 10 seconds, in exactly 10 seconds. In other words, this duck would get nowhere. It would go on a big journey, but it would end up, its distance would be big, but its displacement would be 0 in 10 seconds, right? Because 5 to go up, 5 to come back. Why 5? Because it's being thrown up with 50 meters per second of initial velocity. Why did I make it negative? Because I'm making up negative in this problem because I decided to. Would you get the same answer as I did if you flipped your negative and positives? Yes, you get the same ultimate answer that the duck goes up 105 meters. Like, you would get a positive sign in there, not negative, but that would mean up for you, and the negative meant up for me. And it's 105 meters because it's still going up by the, I mean, it's still above where it was thrown 7 seconds after it was thrown. We would have to put in a time greater than 10 for the thing to be below where it was thrown. All right, I'm over talking that, but that's how that one goes. That's just a free fall problem. Now I'm going to move on. Let me just see if there's anything else in the chat. No, it doesn't look like it. Okay, and I'm going to move. Is there any? Okay, it looks like it's clear to Katie, Claudia, and Maria. Okay, are pretty clear. All right, so I'm going to move on to part C of the duck problem. Okay, this is interesting. Okay. I was going to discuss this anyway, but the problem actually lays it out for us. That is so nice of this problem. Okay. So we have the same thing. Okay. So this is the new situation, and we're still in the elevator and all of that. Okay. First, it asks for a free body diagram of the duck. Okay, so the duck, I'm looking at the pictures. Yeah, the pictures are exactly the same because they should be. Like, the duck is on a platform inside an elevator. This time, though, the platform happens to be a scale. So as far as the free body diagram is concerned, nothing different. Like, instead of the normal force up from a floor, now it's a normal force up from a scale. Who cares? It's a normal force. It's a surface pushing up on the duck's feet. Okay, but then it says compute the acceleration of the duck, as though we could do that, as though we have enough information to do that. Like, why does the problem assume, like, just because it threw a scale in, like, what does that have to do with acceleration? Oh, very good question. I'm just changing the view of the screen. The idea is this: the scale is evidently telling us the magnitude of a force. That's interesting. Like, the scale is in fact indicating, well, what a scale should indicate, which presumably is weight, right? And remember, weight is a force. Weight is measured in newtons. Weight in general actual weight is the downward gravitational pull from center of Earth acting on a mass, right? Every mass near the surface of the Earth has a weight. Mathematically, the weight of every mass is m times g, right? That is a force measured in newtons. That's your actual weight. Now, this scale is doing what it's supposed to. It's measuring weight and it's returning a weight. It's giving a number. And supposedly we're supposed to infer from the number that the scale is saying something about the acceleration of the duck. That seems really weird. Why should the weight have anything to do with the acceleration? Well, let's stop for a minute and think, like, how does so weight equals mg? How does a scale measure this? We stand on a scale. We push down onto the surface of the scale. I'm talking like a bathroom scale, something like that, right? I mean, I don't care if it's digital or analog, but like a platform scale, like in a bathroom. We push down onto the surface of the scale. So what is this force that we're pushing down with? This is called the normal force. This is a normal force, right? So by Newton's third law, if that's the action, the reaction is that the scale pushes up on us the same amount in the opposite direction. So this is the, remember we were doing the action reaction pairs last week. So this is like the action. The reaction therefore the scale exerts an upward normal force on us. They right? I mean, we push down on the scale pushes up on us, or vice versa. The scale pushes up on us, we push down on the scale. They've got to be equal and opposite, right? The scale readout in newtons displays the magnitude of this normal force. I'm saying that the normal force is what the scale actually like I'm saying the scale doesn't directly know your weight. The scale is not the center of Earth. The scale doesn't know anything about, doesn't directly know anything about what anybody's pulling on you. What the scale knows is how much something is pushing on it, right? What the scale reads is the normal force. And this is what you could call apparent weight or measured weight, if you like. I'm saying the scale doesn't directly read your weight. The scale reads something called the normal force, which tells us our weight under typical simple circumstances. Like if and I can scroll back at any time. Sorry, I'm just like trying to explain this. Tell me if you want me to go back a page, any of you, and it's fine. But if we are not accelerating, for example, if we're just like standing in our bathroom on a scale, then normal up minus gravity down equals MA, like we've been saying over and over in this whole duck problem, right? But if we're just standing in our bathroom on a bathroom scale, then A equals 0, and then N equals mg, right? Again, this is where this comment, so N can equal mg. So when we're just standing around under totally like straightforward circumstances, then indeed the normal force magnitude up does equal the weight magnitude down, not because of Newton's third law, but because of Newton's second law, right? But because of Newton's second law, because of Newton's second law, in that case, they're equal. So typically, or so I should say, so often, apparent weight equals actual weight. In other words, scales are often correct. That's why we use them. And you could even say they're always correct as long as the person standing on them is not accelerating up or down. But in the case of this problem, back to the problem now, and again, maybe I'm going, I don't know if I'm going faster than usual. I mean, we said the course is going to speed up, but that if I'm going faster and faster, that's just because I am. It doesn't mean you can't stop me. Maybe for some of you, this is better. I don't know. Back to, if A doesn't equal 0, then we're back to this elevator problem. I'm saying this duck in this, we're going to get the number. I'm just explaining like how we're getting the number from what the scale is saying. I'm saying once you're accelerating in an elevator, scales don't read your normal weight. The bigger the number the scale registers, the more you must be accelerating, or vice versa. The faster you're accelerating up, the bigger the number will register, and the faster you're accelerating down, the lower the number will register. And I am saying this not just about ducks. I mean, I'm saying literally that if you took a bathroom scale into an elevator at John Jay and you stood on that scale, when the elevator is going up or going down at constant velocity, when it's cruising and you feel fine, when you feel nothing, when you feel just Newton's first law, and Galileo's principle, when you can't even tell whether you're moving or not, nothing can tell whether you're moving or not. The laws of physics are the same at all unaccelerated reference frames. So the scale will read your typical weight in newtons, if it's a metric scale, or if it's an American scale, it'll read it in pounds. But pounds are just a conversion factor away from newtons. Pounds are a measurement of weight, of force. When you're in an elevator and it's cruising, the scale will read your weight. But when the elevator starts accelerating up and you feel something in your stomach, or you feel something weird, you cannot tell when the elevator's, this is the big principle of physics, you can't tell when the elevator's moving, but you can, because that doesn't mean anything, but you can tell when it's accelerating. You feel it in your body, you feel it in your, many of us, and some of us feel it more than others, obviously, and we get used to it and all that, but you know it. When something is going on, experiments work out differently when the elevator is accelerating. And one clear indication is that you will feel the floor press against your feet more. And then that force actually will transmit up through your body, into your stomach, whatever. But specifically, the floor will push against your feet more. That's called a normal force. The normal force, just like with the duck earlier, will be greater than your typical weight. So by Newton's third law, you'll push back on the scale greater than your typical weight. And if you were standing on a bathroom scale in an elevator while it was accelerating up, the needle will absolutely move. Like we used to do this at John Jay all the time, except we still could. We have a bathroom scale in the, ask your lab instructor, whatever, whatever. There's a bathroom scale or just ask if you could borrow it and go out of lab for 5 minutes. And I'm causing trouble by saying this, but literally, if you go into the elevator and you stand on a bathroom scale, I promise you, when the elevator, not whenever the elevator is moving, but when it leaves a low floor and starts picking up speed to go to a high floor, or when it's descending into a low floor, when it's slowing, all right, this will totally prove the whole thing from earlier in the semester, or it won't prove anything, but it'll demonstrate what we said early in the semester. If you're accelerating up, which either means the elevator is leaving a low floor, picking up speed, speeding up on its way up, or slowing down on its way down. Either way, the scale will press against your feet more intensely and the weight will register a higher number. It doesn't literally mean the earth is pulling on you more now. You didn't literally gain weight, but your apparent weight, every aspect of weight that we sense, how much you're pressing against the floor, will go up when the elevator is accelerating up, which either means speeding up, moving up, or moving down, slowing down, right? And the converse is true. If the elevator is decelerating, if it's accelerating negatively, if it's either slowing down while reaching a high floor or speeding up while coming into a low floor, the scale will say something lower than your typical weight, or say something lower than it says when you're just standing there. And again, the scale, if it's an American scale, it's probably like in pounds, so you have to convert them to newtons, but all the same thing will happen. So to finish this, and if you, I'm just looking at it, okay, so it seems like this is clear to view. Sort of cool. I think it's cool, whatever. So here in this problem here, with the duck, the ultimate point of this whole thing is like we're trying to, with the duck, we're told that the normal equals 720 newtons, right? And we're trying to find the acceleration of the duck, right? Well, it's the same free body diagram every time in this problem. It's the same free body diagram every time. So it's the same Newton's second law statement every time. N minus mg equals ma, right? But a does not equal 0. A equals, and that's what we're solving for this time, n minus mg over n. Well, n is 720, we're told. And mg is the actual weight of the duck, which is its mass times 9.8. What is its mass? The mass of the duck of the mass is 18, right? So rounding. I'm gonna here. I'll go to the other page. So a. N minus mg equals ma, so a equals n minus mg over m. So in English, the difference, what a really is the difference between between apparent and actual weight, right? That A is that difference between how much is the scale off. The more faster you're accelerating, the more the scale will be off all over M. So the normal force, the apparent weight is 720 newtons. The actual weight is 180 newtons. Right. So that's 540 newtons, I believe. No, sorry, 560. I mean, what am I doing? Yeah, 540. Yeah, 540 newtons. Yeah, sorry. Over 18 kilograms. So A equals 30 meters per second squared, right? Because 18 times 3 is, yeah. Does that make sense? I'm just looking, did I do? Yeah, and frankly, okay. And honestly, because I would like to move on, I'm going to say one more thing about this. I'll look in the chat in a second. I'm going back and forth between screens here, but what I believe is I just verbally answered all the questions in part D and E. Honestly, like I think we're getting good enough as a group that you can. I just explained everything in the reflections and in part E. Like when it's first starting to move, it has upward accelerate. When it first started to move up, start moving, travels, and then it stops moving. Yeah, you press up. Yes, when it's first starting to move, the acceleration is upward. You will feel heavier when it's going upward. When it's in the middle of its journey, the kind of acceleration as is no acceleration. At that time, you feel the same as normal. When the elevator is coming to a stop, it hasn't quite stopped yet, assuming it's on its way up. Then the acceleration is down. You feel lighter than normal. And that was part E. I just said it quickly. Again, you can stop me if you want to. I'm going faster and faster because I'm assuming more and more people can handle it, maybe even want it, but doesn't mean you can't stop me. Part D in the reflections is what I just explained. How does the acceleration of the elevator affect the normal force of the duck? The greater the upward acceleration, the greater the normal force, and the greater the downward acceleration, the lower the normal force. And the normal force, and the key to this whole thing is normal force is what a scale would read. By the way, maybe that's the summary of this whole, one big takeaway of this whole thing is, whenever you're trying to picture normal force, you should picture what a scale would read. Frankly, even if you turn the scale on its side and you slam something into the scale on its side, like a scale is a bunch of springs that the more they get pressed together, the higher the number on the scale reads. Like that's what it is. So a scale is telling you how hard something is pressing against it. That is what the normal force is. That's really the takeaway of this whole. So if you push, I mean, you know this too. Like if someone's standing on a scale, if you're and people even say at the doctor's office to not do weird. Well, at least they tell my 9-year-old son not to do weird things while he's standing. I don't mean weird, but like, he'll like jump around on the scale or like start getting things and they tell him to stop because, right? Because if I go over to my son while he's standing on a scale and I push harder on his head, even though I'm not standing on it, if I push harder on his head, of course the number on the scale is going to go up. The scale doesn't know what you really weigh. The scale knows how much you're pressing against it. This is physics, right? So the scale, the A reads the normal force, but B, if you're ever trying to picture what the heck do we mean by the normal force, we mean what a scale would read, measured in newtons. Hopefully that's clear. I will look in the chat in a second. But I think I've just summarized all of the duck stuff. One last thing, though, to back up. Due to all the above analysis of normal force and apparent weight this is why, all the above is why when we are in free fall, as the duck was in part B, right? Part B of this problem, when we're in free fall, we experience apparent or a sensation of, you know what I'm going to say, I think, I hope. When we're in free fall, how do we feel? What do we feel? What would a scale say? We experience apparent weightlessness, right? When we're in free fall, we're sensational when we're in free fall. When we're in free fall, we have the cool. Wow. A lot of people in the chat. Oh, I'm so pleased. Actually, thank you. Even if you guys are doing that just to be polite, I really do appreciate it. Good. I'm glad. Seriously, Paulina and Maria and Alexis, I do appreciate it. And for those of you who are thinking like they're just being blah, 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 well, thank you for being blah, blah, blah. It beats not being blah, 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 if you know what I'm saying. Like, even if they're lying, but I don't think they're lying, but whatever. Thank you for taking the time to say that in the chat. Means I can retire 1 year earlier, as soon as you guys are done with 204. Just kidding. As soon as I get my son to. Anyway, what I'm now saying is, if you go back to part B, when the elevator was plummeting and the duck was just left to its own devices just to fall freely, then it wasn't touching the scale anymore. Nothing was pressing up against it. So what a scale was reading was 0. Right? The duck was as if having no weight. Now here, this is, I think, actually super interesting. Like, because you've heard this before, like, oh, I'm weightless or whatever. Like, what are we really saying when we say something that's free falling is weightless? It almost sounds like a contradiction, because, like, if you're free falling, it's entirely because of gravity that you're free falling. Like, you're being pulled to the center of the earth by the force of gravity, by your own weight. So, like, you wouldn't be falling at all if you didn't have weight. So it's, in a way, it might seem like the most vivid experience of your weight, but we call it, or we say it's weightless. Why? Well, one thing is, if you trust scales, and you're on and every day you stand on a bathroom scale and check the number, if that's what you're all about. Well, yeah, if you fell off a building while standing on that scale, the number would suddenly say 0. It would, right? Because you wouldn't be pressing into it anymore. You'd both be falling at the same rate. There'd be no contact between you and the scale. It would say 0, right? And then you might, and now, obviously, that's not, like, I wouldn't recommend that as an approach to dieting, but it would say 0. But then you also might say, well, then that's like BS. Like, I mean, I don't, like, literally weigh nothing. Right, you don't. You still have mg, but you don't have n. But why we talk about it as an experience of weightlessness is, think about this now. This is all relativity. It's all Galileo. If, let's say, you fall off, not to be weird, but like you're standing on a scale and then you fall off a building, like a really, really tall building, and like it has like a big water park slide, comfy mattress at the bottom. Like, no one's going to get hurt in the making of this artificial video, okay? But like, you fall off a long building for a long time while you were standing on a scale. So first of all, the scale is going to say 0 now. But second of all, say it's a really long time. So, and you didn't know you were going to, and you have like a bottle of like juice with you, or Celsius, or something. You have a bottle of a beverage and you have a glass, and you start pouring. You're like, well, I might as well, like, you're like, Alice in the rabbit hole. And you're like, might as well get comfy now. Might as well pour myself a cup of tea or whatever. So you start pouring your drink into your cup while you're falling. If you really believe all of this, which I do, and you believe relativity, if you think about it, you start turning that teapot or whatever upside down, expecting the tea to fall out of the teapot into your teacup, right? But it won't. It won't fall into your teacup, right? Because it will fall. I mean, there's nothing to stop the tea from falling down freely at a rate of 9.8, except the pot is already falling down at a rate of 9.8, right? As is your hand, as is everything else. So nothing will fall relative to anything else while you're falling, right? So any experiment you would try to do while falling would be a weightless experiment. Nothing will have any weight relative to anything else. So everything will be in suspension. That is exactly the experience. As you know, you're probably guessing this is about what I'm about to say, and then we're done. Astronauts in orbit, in satellites. I'm not talking about rocket ships while the rocket ships are accelerating. I'm not talking about while the rocket ships blast off. But once astronauts are in a satellite in orbit, then they are just free falling. They just like the moon is just free falling toward the Earth all the time. The moon doesn't have an engine. The moon doesn't have a string pulling it. It's just perpetually accelerating toward Earth. While, and we'll get to this later in a little bit, a tiny bit later in the course, the moon, granted, has a velocity that's pointing at right angles to the acceleration. So while it accelerates in, it velocitizes off on a tangent line, so it keeps whipping around in a circle. And that's what satellites do. Like, no one's saying that you have to free fall. Remember, okay, I'm getting all off on it. But again, this is why we have that homework assignment called free falling up. Free fall does not mean moving down. You could be moving up while you're accelerating down, or you could even be like a projectile, right? You could, like in lab 4, you could be moving to a side while you're accelerating down. And that's what satellites, orbits are. They're perpetually moving to the side while they fall in. It makes a circle. And so anything in a satellite, anything in orbit is in perpetual free fall. Everything in the satellite is in free fall. So all that footage that you see of like the astronauts like floating around and like they have to and like their beverages are like their Tang or whatever they're drinking, it's just like floating around. It's not because there's no gravity. It's not because there's no gravity. It's because everything is under the influence of the same gravity. It's relativity. So bottom line of this whole thing, scales read normal forces. Normal forces tell us our apparent weight. If we're in, and our apparent weight is actually dependent on our acceleration. If we're not accelerating at all, then our apparent weight is our actual weight. But if we're in free fall, our apparent weight is nothing. That's the summary of the whole thing. I don't know if that made, okay. This still makes sense. Okay, still makes sense. Okay. So that's that's the duck problem. Okay, it's 112. So we'll move on. But again, if you have any, I'm happy to take comments on that. All right, let me move on in the sheet, and also I'm going to change the view. Maria's like, yeah, whatever. Wait, okay, hold on. I'm just going there. Okay, but that's the duck. Now, I think, yeah, I'm going to try to sort of more quickly. I want to get to inclined planes into that whole lab thing, the lab 5 thing. But at least one person, I mean, I think it was Claude, asked a question about this problem 5. Oh yeah, this gets us into friction now, so that's good. Okay. All right, let's quickly do. All right, we may not get farther than this today, but that's okay. And you're not having new. We're all still catching up with each other, both with the exam grading and with it. So, just for good or for bad, you don't have new homework tonight. But if you haven't done this one yet, or if you're behind, please do catch up. All right, so we're doing now. This is still homework 8. And you'll notice too, hopefully, even though I'm saying a lot as usual, I'm not really doing the 5-step met. I'm just like giving you answers and thoughts that I think are relevant to these homework things. So, if you're turning in the homework, you still want to do it all correctly. It's not you see what I'm saying? It's not a waste of anybody's time for me still to accept homework from you based on what we're talking about in class, because you still have to expand it out and show all your work, all that. Okay, but here we go. Here's homework 8, problem 5, the double block. And I believe now we say there's friction, right? There's friction now. So I tend to indicate that there's friction by Now, in principle, now, really what we should have done in general, what we would do in the next problems with friction is we would give you mu, like a mu subkinetic and a mu substatic. At this time, when this problem was assigned, like we hadn't gotten into that yet, so it just like tells you the friction force. So that's why it's saying this is a little bit unrealistic, but it's doing that to, anyway, that's what it's doing here. But from here on in, if I gave you a new problem that involved friction, I would tell you the mu. I wouldn't tell you the full force. You would figure out the full force, but okay. All right. Anyway, okay. Okay. A is what's the system schema? Okay. It means what's the system schema of treating M1 and M2 as a system. That is a choice, just to be clear, like as one. That's a choice. We could, the whole purpose of this problem, in a way, is to indicate to you that there's always these choices in physics. And one choice that we make is how far out to zoom or to set our zoom when we're looking at, when we're analyzing a situation. We could, and I think later on in the problem, it does happen that we could just analyze M1 as its own thing, or we could analyze M2 as its own thing. We could draw a system schema, free body diagram, all that of just M2 or just M1. At this point in the problem, it's just asking us to choose to regard M1 as like one big thing attached to each other. And we can get away with that as long as they both have the same acceleration, even if that's zero. If they're two things that are accelerating differently, you cannot treat as one system. But as long as a bunch of things are all accelerating at the same rate, you could treat them as one big M, as long as they all have the same A, because it's all about F net equals MA. So we can choose to collect as many M's into one as we wish, as long as, or I'll say if and only if all share one value of A. Okay, so that's what's happening here. So that said, I'm going to draw a system scheme. We'll look back at the Zoom in one. Sorry, again, I'm going back and forth between screens. So if there's something in the chat, I'll see it in 1 second. So it's A, asking for the system schema. Yeah. So of the whole thing. So this is what I would do. I would say my focus of the whole thing. So this is system schema. My focus of the whole thing is M1 plus M2, right? So what is exerting forces on that? Well, the center of Earth definitely is exerting forces on that. And then anything or everything touching that M1, M2 system. So the table is touching the M1, M2 system. The table is a surface that is pushing against the surface of M1 and M2. So it's definitely exerting ultimately what we call a normal force. But I think here we're pretty much told, we are told that there's going to be friction as well. So we care about both of those forces being exerted by the table onto the masses. So this is a case, right, where you put the double line in. Right, like that would be the only thing we could accept if this were an exam. The table mass pair or interaction is really two distinct interactions, one perpendicular to the plane of contact and one parallel to the plane of contact, right? Whenever you have rough surfaces, you make two lines, and we are told that these surfaces are rough. Earth is always one line, and then anything else touching would be one line for every touch, right? That's the rule of system schema. So that's my system schema. Let me just, and then I'm going to do a free body diagram is part B. And then I'm going to look back at the chat just to make sure I'm not trying to discourage. The faster I go, the more it just means it's on you to, and maybe I'm not going that fast. I'm just talking fast. So In part B, we want the free body diagram based on that. Let me just look in the chat. Oh, there is a question. Okay, sorry. No. Good. Thank you. Oh, 7 minutes ago. I'm sorry. I knew that was going to happen. All right, I'm looking at the question right now. Should we be doing the Yeah. Wait. Oh, no, this is a great question. Sorry, it was 8 minutes ago. But Maria's question about should we be doing a 5-step method for the questions that say draw a FBD or system schema, or should the answers just be our drawings? That's a really important question. And the answer is yes, you still have to do the 5-step method. You still have to do step 1 DFP. And I will tell you why specifically. Like, it's even more important here as these go on. I'm really glad you asked. The diagrams, like free body diagrams and system schemas, those are analytical solution tools, just like vectors, okay? Like the system schema even, but then especially the free body diagram and especially the component diagrams, those are all already attempts to start solving the problem. But even before you do any of those, and I should be doing it here, I'm just trying to move faster as like the teacher. But even before we put the system schema, when you present the problem to me, like if you were on an exam or whatever, you should have a picture like the one in the sheet, right? Like the one in the sheet, but with everything labeled. Like the problem with that sheet thing is it's mentioning all the stuff about friction, but it's really like hard to read. Like there should be a label on the table that says like friction equals whatever, and make the table rough like I did. What I'm trying to say is you first want a picture of the facts, even of the problem itself, even before you start making diagrams that solve the problem. And the main reason why, well, first of all, so that you label, so all the facts and constants and variables that you're going to use in your math all get labeled in that picture. But like most important of all, you're going to see when we start getting into pendulums and things like that, you need to draw a picture to show the orientation of the situation so that your diagrams like are like, so that, and then the diagrams are consistent with that. I mean, bottom line, classic example, say we were looking at a pendulum, right? You'd have to draw a picture of the pendulum saying, okay, the pendulum's going like this, so that then later in your free body diagram, when you draw an upward arrow, or better yet, like what you've done in the lab already, like if you have an inclined plane, you draw that the inclined plane is going like this, then I know later when you show me a normal force that's going like, I can't do it with my hand, but that, like later in the diagram, your normal force has to be literally perpendicular to the plane. But I don't know if that's right or wrong or what's going on unless I first see which way the plane is going. Like, so I'm saying all your diagrams, your solution diagrams are all derived from or based on, first and foremost, a step 1 picture that lays out the facts. I'm sure you got, I'm going to look in the chat again, but for everybody, it's like so important. And yeah, I mean, I'm seeing like this kind of issue already kind of in some of the midterm exams and stuff. The step 1 DFP lays out the facts of the problem. Then you do okay, that's even true in, it's like the free float problem in the midterm exam. Like first you're showing me the situation, then you have to do a million triangles to like solve it. But the triangles don't mean anything unless I have a reference guide of the fact. So okay, long answer, but super important question. Yes, we need a picture first before we get into the system schemas, etc. If you're lucky enough that the problem gave you a picture, that's a good basis. Go with, like, at least use that as your starting point, but often you still have to add to that. But if this always happens on the first midterm of 204, to be super honest, just so you guys know, like in 204, this is all true in 204 as well. It's all true in 204 as well. And sometimes in 204, you get these questions that seem really mathy and they don't provide a diagram in the question. It's all the more reason you have to be in the habit of making your own diagrams. Otherwise, the math gets totally low. Okay, that was way too long of an answer, but that is my answer. Let me just look in the chat. Okay, what about the definition? Yeah. I mean, oh, absolutely. So I'm looking at Maria's follow-up. Step three, if nothing else, the big step 3 that you're going to write like every time is Newton's second law. Like sum of the F's equals MA. And you're going to write like as a vector equation. That's like, because that's what we're ultimately solving for each time. and you're going to break it. So yeah, F net equals ma, but often there'll be something, say friction's involved. Then one of the things you're going to do in step 3 is write like friction equals mu times the normal. Those equations are definitely like the step 3 truths that we then do a bunch of manipulations in step 4. To be super, and again, if I sound intense, it's just because I am, but it's a really important set of questions that Maria's asking, and she or others can keep following up on them. Let me tell you, really, the 5-step method in the first place actually was kind of invented with Newton's laws in mind. I mean, it's because Newton's laws are, okay, I'm always so defensive. Why am I a used car salesman? I don't know. But actually, the 5-step method is particularly apt for Newton's law problems because Newton's law problems, actually now physics starts to look harder but get easier in this way. With Newton, there's a lot more going on now than there was in physics like a month ago. There is. But the thing is, with Newton's law problems, there actually is a procedure that if you actually follow it, you don't have to do as much original thinking or fresh inventive thinking. Like, again, I'm just assuming for the common issue in physics is that people not everybody, not all the time, but commonly people say, I can follow it when you Yaverbaum or someone does it in class, it makes sense in class, but then when I go home and I have to do it on my own, it doesn't, every problem looks totally new. It doesn't look like what you talked about in class. So I don't know what to do. Like, common problem. It's nobody, like, that is the way. If you ever feel that way, you're not crazy. And I'm not a bad person. Like, that is how physics feels. But the corollary to that is that people say, if they're practicing and doing work and stuff, they say, I can do the problems, actually. I even can do the problems. And once they're started off, once they get set up and stuff, then I can do the problems. But it's like knowing how to start or setting them up. That's the issue. And fair enough. But that's sort of why we have the 5-step method and blah, blah, blah. But the truth is that issue is much more true in the early units of Physics 203, and it discourages people and it loses some people in the shuffle, blah, 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 blah. But actually, if you really pay attention to the Newton's law stuff and the 5-step method, there's really literally an algorithm here that you actually can follow, and you don't have to think as much with this stuff as you kind of have to think and pull things out of the air with kinematics. Like, honestly, okay, I'm over talking this, but I'm saying more than anywhere, you really want to do the 5-step method with Newton's law problems, because if you really get used to it, step 1, step 2, and if you really get used to the fact that really honestly, step 3 is writing down the laws, and then step 4 really is a bunch of these breaking down these 3 different types of diagrams: system schema, free body diagram, component diagram. Like, we could not ask any of that if we just said, what's the acceleration? If you just did all of that, and then applied Newton's second law to each axis independently, you would get the answer without really having to think of anything new or original. Okay, long answer, but I'm very glad. It seems like this lends itself less. It actually lends itself more. Okay, sorry. Okay. Thank you, DW. I don't even know. Okay, good. Thank you. Sorry to talk about it so much, but it was a great question. The louder I get, and now it's 1:30. Okay. Okay, well, so here's a free body diagram for this one. We'll pick up on this Wednesday, obviously, from where there's no new homework because I'm whatever. But the free body diagram for this one would be normal up, mg down, friction to the left. Oh, wait, was there a hand or something in this? Hold on. I know we've like a minute and a half left. Hold on, sorry. Wait. Oh, there's a hand. See, now this is exactly why we should have drawn a picture. See, there isn't even a hand in the picture on the sheet. I'm so sorry. I didn't do this on purpose, but I didn't even read carefully enough, and I didn't even portray. There's a hand in this picture, which we definitely would have wanted in the. There's a hand in this problem. Sorry. So we're going to end on this, but wait, hand, it just does. Okay, so I cannot draw hands. Anybody that can draw knows that hands are hard and I can't even draw. So there's my hand. Okay, I'm sorry. It's pushing to the left, or it could have been pulling on the other side, but it's going to the left, right? So there is one more thing in the system schema. Sorry, we're ending on this. But that just shows you, hopefully, the power of Maria's question, maybe. So there's a hand. And it's either pushing or let's even say, you could even say it's pulling, make it even easier. But it's not exerting independent friction or anything like that. So that's just another force. And so, sorry, so the friction's going the other way. The hand is going that way. And we have no reason, I haven't read enough, we have no reason to believe that they're equal and opposite. I'm going to assume that the hand is winning for the moment. It could either be the tension pulling from a hand or the normal. Anyway, that's the free body diagram. I'm not assuming there anything is equal and not. I'm not assuming that the horizontal forces are equal and opposite. The vertical forces, I'm assuming, are, so this goes back to Claudia's thing. I assume that the normal force up supports the entire weight of the whole thing, M1G plus M2G. And literally, literally is the last thing I am saying today. For good or for bad, that is class. I'll hang out for a second if there are questions, but have a great 2 days. Don't do any more homework. Okay. Have a good day. Have a good day. Okay. And I will stop the recording. Okay. Yes. Thank you so much. Have a great day. Awesome. Thank you for your feedback. Thank you everybody for participating the way that you did, or thank you all that did. Stop the recording. Stop the madness. Put down the cannoli. Yes. Have a great day. Thank you.